In April of 1961, I'll ask you these questions. Who was the first person in space?
Yuri
Gagarin, right.
Yeah.
On the Vostok. Okay, it's going to get tougher. Okay. 1 month later, who was the next person in space? Right, okay. Who was the third person in space in June of 1963? No.
Gus Grissom?
No. It was a Russian woman.
Yeah.
It was a Russian woman who went, Valentina something, I forgot what her name is. Anyway, that's it. There was another space program going on. And 1 month later, in July of 1963, that space program launched its fellow into the edge of space. What was that about? Anyone know what that was? You're old enough to know. It was my favorite, coolest thing in the 60s. What was the craft called?
Gemini?
Okay. Give up. X-15. The X-15 program was an ongoing program. They actually then canceled that and pushed the money into the Mercury program, Gemini, Apollo, and that sort of thing. And the fellow who flew it, they actually flew 354,200 miles up. I think that's 67 miles to the edge of space. It was Joseph Walker who did that. We never hear about those astronauts. And the reason you don't hear about those astronauts is because they were actually test pilots, and NASA never gave astronaut wings to test pilots. They gave it in like 2005 or 7 after they had passed away. Just an interesting little tidbit. Tonight, we have the honor of having Dr. Haimin Wang. Okay, he is the NJAA Distinguished Professor of Physics. He's an Associate Director for the Center of Solar Research and the Big Bear Solar Observatory in California. You have to Google that sometime and see that. It's an awesome, amazing place. So please welcome Dr. Wang.
Okay. Thank you so much for giving me this opportunity to speak about one special star, which is very different from what we observe here, right? We observe at night, so we don't see that star. So that star is our sun. Okay. But there is a unique feature of the sun, which is you can look at it in detail. So there are a lot of physics we can learn from the observation of the sun. And in the last few years, actually I did see a sun here. This is the sun, right? And they're back over there. Oh, okay. So you're probably aware of that in the recent years. It becomes national interest. Starting with President Obama, they issued an act called the National Space Weather Act. So maybe 30 years ago, we don't have this concept because at that time, the telecommunication or the computers are not that sensitive. But today, if there is any eruption from the sun that can disturb the Earth's magnetosphere and also the other part of the Earth, that can cause a lot of effects. That effect called a space weather. So there is a branch in study of the sun. It's called space weather research. So that becomes a very important part of that is to understand it. So we have two functions of the solar astronomers. One is to understand the basic physics of it, since we can magnify the sun to look at detail. The other thing is trying to predict, just like a weatherman. The weatherman, you can predict if there is any snow, or today the heavy rain. And for the solar physicists, we also predict if there is any solar eruption and a possible space weather consequence of it. So this branch is called space weather research. Okay. Since I hope this talk will be somehow informal, so that means you can interrupt me at any time if you have any question or if I didn't explain things clearly. Okay. So the the title of my talk shows that I'm going to talk about this solar telescope. It's a 1.6 meter telescope in California. I will talk a little bit about history, why we are New Jersey, we are linked to California. Okay. And this telescope is named after another professor at NJAA, Professor Fairgoody, and he contributed significantly in building this new telescope. It was built almost 10 years ago. This picture is taken in California. It's in a very beautiful lake called Big Bear Lake. The first thing, so I just want to, this is a winter view of the, it's in the summer, it's a very nice place for the water sports like boating and some other water sports. And in the winter, it's a ski resort. So it's a very nice place, okay? This observatory did not belong to New Jersey many years ago. It was built by Caltech, so where I got my PhD, and I did my PhD thesis in this observatory when I was a graduate student there. This was a contribution of my thesis advisor to the entire solar physics area. In previously, people built the observatory on high mountain, you know, trying to get a clear atmosphere, and probably some high mountain, the weather is also good, okay? And my advisor found that actually building an observatory in the middle of the lake is actually very good for solar observation. The reason is, if you observe the sun is a very strong heat source. If you go to the desert, you will see that. In the summer, the desert, you can see kind of whatever in front of you is got distorted. It's just due to the turbulence of the hot air that comes from the sun. Okay, so then my advisor did a site survey for like 200 sites in Southern California, and found that if you put a device in the middle of the lake, is water stabilize the temperature. You can eliminate those, not eliminate completely, minimize the turbulence. Okay, so this is why they choose the Big Bear Lake because it stabilizes so-called scene. At nighttime, this concept, this problem is not as big as during the daytime, because at nighttime, the sun is not there, the temperature is relatively cooler. So for the nighttime observatory, most of the time is still in a high mountain, not in a lake. Okay, this is a history. In 1969, the observatory was built. But then in 1995, actually it's 1997, Caltech decided that they need to focus their research on nighttime astronomy, especially at that time. You probably heard of Keck telescope, those 10-meter Keck telescopes they built. So they're trying to focus on those areas. So decided to find a partner to operate their solar physics community, solar physics solar telescope. So then New Jersey becomes their partner. Since I moved to New Jersey and worked with Professor Goody, and we decided to take over the operation. Now you can understand that the operation is very difficult, right? Since our base is in New Jersey and our observatory is in California, just exactly across the country. In the beginning, it was you know, a lot of burden for everybody, but now becomes quite stabilized, since we have many graduate students and postdocs. They probably add together more than 10 of them, so just fly back and forth. Each one take a couple of weeks of the time. Okay, so after we took over during the last 20 years, we built this 1.6 meter telescope. When Caltech had a Big Bear, the largest telescope was 26 inches. So this is like more like 60 centimeter, more or less like the one upstairs here, right? Very similar to here. So we changed that. Now it's 1.6 meter with the support of many places like NASA, National Science Foundation, as well as Air Force. So that's it cost about $20 million. The first light was in 2009. Okay, so it's almost. But during the last few years, we did a lot of updates. So it's at this moment, it's biggest solar telescope in the world, 1.6 meter. I mean, 1.6 meter is not biggest for the telescope, but for solar telescope, it's the largest. Until in 2 years, the National Solar Observatory, that's a national project. We are also part of that. They are building a 4-meter solar telescope in Hawaii. Okay, so we are looking forward to seeing that. But still, even after they finish a 4-meter telescope, we should be able to do a lot of unique things they cannot do. So it still will become a very good facility. The reason is Big Bear, because of this lakeside, we can get a stable atmosphere for like 5 or 6 hours a day for most of the days during the year. But in Hawaii, they don't have that condition. So we can, for things, especially we look at a so-called solar activity, which I will also focus on today's talk. And you will see we needed this long, stable atmosphere. Okay, so those are the all the images. I mean, not the all, selected images we have. And this is not the whole sun. This is only a part of the sun. It's a very small part of that. I will show some later. This is the entire disk. And I also noted in your picture here, most of the prominent things on your wall here are sunspots. So that we also can magnify it. Okay. So because we have this largest telescope, we have made quite a few discoveries in the last few years. I just want to mention one thing that we had for the solar observation is we have a stable atmosphere. Actually, no matter how stable, you cannot get with the resolution of our atmosphere, you cannot get anything better than 0.5 arc second. Probably you also use this concept of arc second. So on the surface of the sun, each arc second is around 1,000 kilometers. a little bit smaller. It's only 730 to be exact. Okay, so that means because of the atmosphere, if you only look at the resolution, you anything above any telescope above 25 centimeter, that's like 10-inch telescope. Anything larger than that doesn't help you because of the atmosphere. The atmosphere cannot make you see clearly. If you build a 5-meter telescope, you still only see what the 10-inch can see, the 25 centimeter can see. It's just atom turbulence is your enemy. So how to solve this problem? Of course, the better the observing site, like Big Bear, the chance to get a higher resolution is larger. And then there is, this is also only developed for solar observations in the last 10 years. It's called adaptive optics. So this is a very, very much advanced technology. Actually, it's a military technology, so that's why that cannot be, that kind of technology cannot be exported to other countries. So basic idea is the because of the atmosphere, we're trying to find a correction for the atmosphere. What we do is we divide your telescope into many small pieces, not really cut it, but we do an imaging. That's called a wavefront sensing. We basically trying to see what kind of turbulence is created. And then we can simulate this turbulence. We simulated this turbulence through a high-speed computer. And then we feed this information we derived for the turbulence, and we control a deformable mirror. So that means there is a mirror. We divide that into many, many small pieces. And in the back of each one, we have an actuator. They're trying to poke it. And this, so then we correct the so-called wavefront, distorted wavefront. If basic idea is just you divide your big telescope into many small pieces and make it like a rubber mirror. And then we correct the rubber mirror, and then that will correct the distorted wavefront. And then the image will be diffraction limited according to the aperture of the telescope. So this is a very much advanced technology. So this is basically the setup of our telescope. I just only pick up a few important things. It's a refractor. And all the light, then the primary mirror is right here. Then finally it's going to called a Coulomb bench. So that's where the no matter how you rotate, this beam won't be changed. It's called a Coulomb bench. That's fixed into the platform downstairs. So we have a lot of focal plane instruments right there. Basically they are CCD cameras. Okay, so I just want to mention a couple of things that we do. Since their instruments are very complicated. Now one is measurement of the magnetic field. This is a very, very important thing for solar observations. So basic principle is very simple. It's using an effect discovered by Haimin, called the Haimin effect. That's immediately after that basically just said that one atmospheric line is split maybe into two or more if it goes through a magnetic field. As soon as that effect is discovered in the early 20th century, then the Caltech scientists used that in Mount Wilson. They found the sunspots have very strong magnetic fields of a few thousand Gauss. This is so we still now we are using this to get a more and more detail of the magnetic fields on the sun. And but the wavelengths we use, it's not in the visible. You know, while we see the visible light, we use so-called angstrom as a unit. It's like 5,000, 6,000 angstrom, and that's most of the astronomers using. A Big Bear for the magnetic field measurement, we use a near infrared. There are a number of reasons there. The one primary reason is there are a couple of very good spectral lines to look at the magnetic field. They're so-called magnetically sensitive. The other reason is in the near infrared, the seeing is it's relatively stable. Okay, but also we have some other observations in the visible wavelength. The advantage of the visible wavelengths is shorter wavelengths, you have a higher resolution. So that's the basic concept. There is another instrument. It's not working yet. We are trying hard. It's a very, very expensive instrument. This is an observation in the middle infrared, like 4 micron. Okay, so the whole system is chilled to a very low temperature. The one important thing now we're looking at that is also look at some discovery is on the sun, the surface temperature is usually around 6,000 degrees, but some area is actually very cool. It's only like 3,000 degrees. But of course, the standard cool is comparing with the solar surface itself, like it's cool, 3,000 degrees. In those areas, you have some molecule lines. So when it's too hot, you don't have molecule anymore. They're all dissolved. And when it's too hot, you don't have molecule. Only when its temperature drops, you have a carbon monoxide. So that's the line that we use. But anyway, that system, we wish it would be working in a year. Then we probably can look at a very cool surface of the sun. Okay, like inside the sunspots. Okay. But anyway, those are the real optic table, but I'm not going to go to detail. And so now with the adaptive optics and without adaptive optics, you can see the difference. Okay, we of course, with adaptive optics, we also use some image processing that we look at very detailed. So those images are clearest solar image ever observed. Nobody else had it except the NJAA's Big Bear Solar Observatory. So this is a unique thing that we have. Because of the time, I'm not going through. I probably just show you this latest advances. So those are the older classical adaptive optics. In last year, we created a new one. You can see there's switch between those two. It's called a multi-conjugate adaptive optics. We put 2 layers of the wavefront sensing. Since atmosphere turbulence could come from different layers, we know where the classical one is 1 layer. Now this becomes even sharper, become 2 layer. So probably that's all I want to talk about adaptive optics. I skipped to another very cool concept that we use. We use one spectral line that's very useful. It's for the hydrogen alpha line. This is this comes from the hydrogen atom. It's pretty much from the 2nd to 3rd energy level of the hydrogen. And we use those Fabry-proof filter. They basically, you can tune different line positions. And this is a demonstration of the different line positions. And when you go to the center, you can see a lot more structure. You see higher up in the atmosphere. When you go to the wing, you go to the lower atmosphere. So this technology, there's a special term of this technology. It's called imaging spectroscopy. It's not the spectrum that you use a grading system, but instead you use Fabric Pro to tune the filter, and you can get an image at the same time. You can get 2D image at the same time, and you can tune the filter very quickly. So that means for every position, you can find the spectrum profile. From spectrum profile, you can measure a lot of things like speed, like the density, like temperature. Okay. So I skipped a few instruments that we use. I will focus on a few discoveries we made that might be very interesting. From the in the last few years, we had this NJAA group had over 100 publications, including a few Nature publications that make NJAA to be the solar physics group to be on the very top of the internationally. So we are proud of that. We bring something set the best for New Jersey locally in NJAA. Okay, immediately what we see from the observation. Again, I emphasize this. Suppose we see the sun right here. This field of view is from here to here. It's only 20 arcsecond. Probably, just barely like 20 arcsecond. From the diameter of the sun, you probably know it's 2,000 arcsecond. Diameter of the sun. This is 20. So if this is the sun, the magnified area is 1% in the diameter. So that probably is just barely it's not even a sunspot size. So that's how we magnify that. As soon as we magnify that, we found the things that people call a flux loop. This is a very important thing for the solar eruption. And for first time, we really can identify that. It's what happens is on the sun, it's you have many magnetic fields that got twisted very heavily, okay? And when that twisted too much, you know what will happen? It's going to break. This is exactly what the solar flare can happen. It's you have magnetic fields, they are like a loop. They got twisted. So we give a name called a flux loop. So this is our very first Nature paper we describe as the characteristic of the magnetic flux loop as observed in high resolution. So this is potentially very important to understand the mechanism of those solar flares. Okay. And this is the year after that, we published a Nature Scientific report. Before our study, this is what from the space telescope, this is the whole sun. The flare just have two bright ribbons. This is all what we can see. But with the Big Bear observation, then we start to see many things for this flare. We still see two flare ribbons. This is probably the best observed flare ever. You can see the two flare ribbons. One moved to left, the other kind of moved to right, right? And then now we can see on top of that, they call post-flare loops. So there are a few very cool things we found. The one thing I will mention a little later is before those two ribbons appear, there are some precursors. They're shown here 1 and 2, and then flare happens. This is very important to understand to do a prediction if we have those precursors. So I will talk about the magnetic structure later. And another thing is for those are called post-flare loops. Then we found that they can create a secondary brightening. So what happens is there are magnetic fields above the surface. What the flare is, you have those loops I just mentioned. They start to break. When they break, they're cutting through those magnetic fields. And those magnetic fields reconnect. And they reconnect at a higher and higher altitude. And because of reconnection, they accelerate some electron. And the electron move down, they hit the atmosphere. Sounds like a very complicated process, right? So it's just due to the basically breaking of the flux loop, and that can open the magnetic fields, and then they create those flare ribbons. So but our discovery shown that even after flare, you have very small amount of energy release. So this is actually very important. It's not just for flare science, but those kind of small energy release later on we found can contribute to a similar physics problem that people are trying to explain. In the surface of the sun, the temperature is few thousand degrees. When you go a little bit higher, you probably know what the temperature of the sun would be. It's actually getting higher. That's getting into 1,000,000 degrees. So this is a very famous question called a corona heating problem. In a solar corona, it's heated to 1,000,000 degrees. So now we found that those small-scale energy release in this kind of format might be very important for the solar corona mass ejection. Okay. We also found another very interesting thing. I probably show the movie only. We observe another wavelength. It's a helium. Then we found in front of flare, there is a dark ribbon. This is surprising. We saw flare is energy release, always on the heated atmosphere. Then we found this is not only in one event, and we found in many events there is a dark ribbon. And actually, we found that actually this was predicted many years ago by my physics advisor, like 40 years ago. He predicted that. You probably will found. I'm not going to talk about the physics of it. It's basically related with in the ribbon front, the electrons streaming down, then they ionize helium. And when they come back, those electrons, they form a different kind of helium. So I'm not going to tell you exactly what the equations is, but I just say it's due to ionization of the helium. So that can be, so that means our observation with the highest resolution can confirm some theory 40 years ago. So never been observed, now we observed. And also we found that if you don't have such a resolution, these ribbons are so narrow, you don't see it. Okay, it's only with this high resolution. Okay, this is another. Okay, now let's talk to you